If no one's ever done it before, then I don't really have to compare against anything, right? So no one had actually solved this problem. So we didn't have a performance comparison, like my accuracy for detection was this or that, right? When you're looking at trying to design a research goal, actually the DARPA program sort of view, right? No one has done what you're doing, right? But you still want to think about these are the measures we should be looking at, right? And so you want to find that balance of what's the right experimentation. So, but he actually did a really good job in the sense of like, well, here's what it is. Now let's go see. He didn't just say, here's our privacy solution, see logically it works. He said, well, can we detect it? He didn't say, see, it now works, it's hiding in Skype. He asked the question, can I detect it in my, with even a simple detector, showed that it could, and then showed how to address those concerns. So that's the kind of thing where a good experimentation process, right? Did he start his research that way? Don't know, didn't ask him if he knew he was going to get to that, but trying to build a detector was a natural thing to want to do given the kind of problem he was looking at. But the variability, so now back to the experimentation part of our lecture, variability is often there, right? So if I actually think literally about different traffic schemes, right? If I try to figure out which one of these was his traffic and which one was not, it'd be very hard because there's so much variation, I can't distinguish them. So if I go back and I ask that question, so what happens if I average them? I said, well, if I just average them. So here's the average of 3, reinforcement learning, the knowledge base, which I think was KBS, it might be something else, and SVM, right? If I look at those performances number, right, now, is one better than the other? There is so much variation, it is very hard to tell. Okay, in fact, if I look at the differences about those, and I then take the average performance, statistically, there's nothing that is a significant difference. Because they all bounce up and down so much that none of these are statistically any better than the other. Now, if I can do some things, right? So what might I do to try and answer the question, is one of these better, right, given this data? And so I averaged it, that didn't answer. What else might I do?
You can look at an integration of every point along the various curves to see if
right.
there's one which is a percentage better.
Right. So we could do what's a cumulative distribution transformation, right, which is accumulate data this way. I could do a simpler one, which is also just sort of bin them, put them in groups, sort of say, okay, effectively, I average one way, maybe I average this way as well. So if I average that way, right, now I get, okay, 3 points for the green one, right? I reduce the number of points, and I reduce how much they bounce up and down. Unfortunately, still none of those differences are statistically significant. This large trend is much greater than these bounces here, and it's not enough to answer this. So when we're looking at things, okay, if we're trying to look at what's going on, why are these things not significant? This comes back to one of the lessons from the beginning of today's talk, which is that most explanations involve additional factors. In fact, the most interesting ones almost always involve additional factors. It's the additional factors, like the additional details in a story, that add color and make things more interesting. So here I have a problem where the means are close together and the variance is high. Here's another one where the means are farther apart, but the variance is higher. Which of those two is more significant? I have no idea, right? So the answer is, right, you can do a lot of calculations, right, and guess, but I'm going to guess, right, from those, it really is just a guess, right? So here, right, I'm farther down, but there's a lot more spread in them, right? So the integral of this piece is actually, so this one is probably more significant because the chances are random, the integral into this tail is less than the integral into that tail. That's really what chance is. If I look at the two overlaps, what's the cumulative probability that one of them could have been on the other side and I just didn't see it? Okay. Right. So I happen to get the unlucky sample over here, right? So a lot of winners are unlucky samples. Right? They're actually lucky in one sense, but from the distribution point of view, they are an unlucky sample. They're extremely unlikely to occur. They're an outlier. So when I'm looking at things and I have a lot of variation, right, it looks like things are happening, but things will change. So one of the things that can happen is if I really have, as in this plot, a trend, if I've not accounted for the trending, then the reinforcement learning algorithm has itself a lot of change. It changed 3 steps. Well, is that random or is that real, right? Every time we try to reduce this, right, we were reducing things, right? We reduced it here, right? This reduced it from the previous slide, but it's, well, you lose visibility in the data, but in terms of the variation, right, there's a lot of variation here. So the question is not just the variation up and down. It turns out that we as a human look at this and we see a trend, right? Almost every one of you, when I first put up this slide, said, oh, look, REL is definitely better, right? Why? Because it's everywhere better than the others. Now, the answer of whether or not REL is better than SVM, right, depends on also what test I use. We'll come back to that when we get to the next class. But the fact that it's increasing makes it difficult because it means REL has a lot of variation and SVM has a lot of variation, which tends to put me in this category. I have so much variation, it's really hard to tell. Right? It might actually be that this is more meaningful, but there's such a large variation, I can't conclude for sure. So lesson 2, one of our goals is to design your experiment to explain or reduce the variability. We want to find and control what's causing that variation, right? So our linear trend was much greater than the internal variance. So we want to try to find a way to reduce that. So coming back to the other lesson, 7, we can look at this and sort of say, okay, what's causing this, right? And look at the data from a human point of view and see what's going on. So if I were to say, what contributes more to the variance and accuracy scores? The subject, person 1, 2, or 3, versus the algorithm. Right? Just look at the plots here. So we have subject 1 and subject 2 for SVM, REL, just SVM and REL, right? So here's subject 2, here's subject 2, here's subject 1, here's subject 1. What's causing more variation? Subjects, people, okay? And this is a classic problem. Anytime I have lots of people involved, they're probably one of our largest sources of variation. So if we're looking at that, we can now say, okay, can we look at what kinds of errors we have? So in this problem, which was putting mail in proper folders, right? This is like automatic mail foldering, which spam would just be one of the folders. But, so there's really 3 categories of errors that can be identified. If I went back and looked at what was going on, why is subject 2 have such a low accuracy? Well, there's a number of things that happen where folders were, the data was misfoldered. I literally dragged it and dropped it into the wrong folder. But once it's been labeled by being in the wrong folder, it's going to really mess stuff up. So my folders are a mess. My mail folders really are a mess. I actually only have one consistent algorithm, time. Any other label I give stuff is just broken, so I just give up and just use time for almost everything. They can also have this kind of error, which is called non-stationary. This is a classic problem for data that changes over time. The folder I put it in today, the folder I put it in a month from now may not be the same, or going backwards in time. Where I would have put it a month ago, I might have even had the folder. Now it would go in a new folder, right? Because as I see a trend, I start generating folders, and I may not move old stuff in, so they might get messed up. And then things that are ambiguous, right? They could have been in other folders, right? It's both departmental work and committee work. Does it go in the committee folder or the department work folder, right? Or you duplicate it and put it in both so you can find it. So users found in the analysis that underlied this project, between 40 and 55% of the messages fell into one of those 3 categories. So you basically said humans can't answer this question, and now I'm going to make my machine learning algorithm try and answer it, and I'm going to evaluate it against how well humans do. So if humans can't answer the question 50% of the time, you're limiting how well your machine learning will probably work. Not oddly enough, turns out you can do much better than the 50%. If the human errors are consistent, right, then you might actually come up with a pattern that is better than any one human on average over lots of humans, because they make errors in groups, but it doesn't always work out that way. So when we look at this, we're sort of exploring the data, and you start looking at now, the insight to look at it by subject was not obvious, right? When we looked at this, there was nothing, when we looked at this, right? There was nothing telling us we should look at it by humans. But anytime you have additional factors, right, that's what you start doing here. Exploratory data analysis is break the data up by different ways. In one of my own PhD students' research, we ended up doing an analysis by day of the week for something that shouldn't, it was a computer looking at the computer screen of another computer. Nothing in that really suggests the day of the week should matter. But it turns out it mattered a lot for our system. It mattered a lot.
Mondays are bad for everyone.
Mondays were bad, but we were actually, so this was a computer looking like we were trying to do face recognition. And it turns out that the day of the week mattered because it mattered when the factory that was nearby our campus was outputting more smoke or not. And it changed how clear the air was and how much stuff accumulated on our screens. Okay. And I had another student whose exploratory analysis found out that on days he collected data alone when I wasn't in the lab and I didn't set the experiment up, he got very different results than on the experiments I had set up, right? Which is not, again, something that was like, what's going on here? So when I set up the cameras, so this was a long time ago, we had cables that were BNC for Ethernet and cables that were BNC for video, but the two had very different impedances. So I would continually set them up using proper video cables, and he would set up his experiments using network cables. They connected, they worked fine, but they produced very different results, right? So exploratory data analysis is often about finding things that were wrong that you didn't know about, or things that you weren't even thinking about that drive your experiments crazy. So although humans are one of the first places you should look, right? It could also be that time of day affects how hot your computer is. There's a ton of things that can go wrong. So my recommendation when you're doing your first pilot test is you collect a ton of variables that you will hopefully never look at, but log all kinds of stuff, because if you don't log it, you can't figure it out. Those cable experiments, it took us 4 months of repeating experiments and not getting consistent results before we eventually figured out that I was setting the cameras up differently than he was.
There's also a really unusual thing that happens, both with decreasing variability and increasing accuracy, which is that if you ask 10 people or 100 people the same question, they'll tend to regress towards a mean that is on average better than the individual guesses. Wisdom of the crowd model. So there's a whole bunch of psychological studies on how that works.
So
there's a way of decreasing variability as well as presumably increasing accuracy.
So if you regress towards the mean, then you reach the average. So I'm not quite sure exactly what you're saying there, but
so let's use the classic jelly bean experiment.
Mhm.
So if you ask 20 people in a room the number of jelly beans in the jar, what happens is if you take all their averages, it will actually probably be more close to the actual number of jelly beans in the jar than any one guess.
oh, then any one guess, yes, right. So, but you said it regresses to the mean, therefore it's better than the average.
Oh, no, sorry.
It regresses to the mean. The average is better than
Yes, the average is the average.
Okay, so now, so when we're looking at this, although here we had the one example, right? Look for all kinds of things that help explain why there's variability in your data. So the nice thing about this is you don't have to be looking at this entirely as, does my theory work? And I'm looking for random things to break my theory. I'm looking for variability of the data, which actually makes it pretty easy, because if the data isn't constant, it varies. Right? So I don't have to have any deep theories. I just look at my data, look at the performance variable, and figure out, is it constant? And if it's not constant, then I want to come up with a transformation. Now, this is looking at other factors, but last time when we looked at the ring, right, we came up with a transformation that tried to make the data variable, right? So in this one, we might actually get to that in the future, right? But in this one here, what's one of the things I might actually try and do to reduce variance besides dealing with people?
Only using the data in this slide.
Yeah, only just looking at it. This is just an example, right? But what does this slide suggest?
That accuracy globally increases as
Right.
training instances.
In fact, with only 3 points, so it's hard to tell, right? But it looks like it linearly increases or some other increasing function of the number of samples. So that maybe if I come up with a transformation that tries to look not at accuracy, but as accuracy per sample or something, right? I can try and make this line flatter. Right? Anytime I try and make my performance line flatter, then I will have a lower thing. This is, again, statistical terms. We're going to do statistics next week, so we'll eventually go through all these terms. But of sample variance, effect size, and sample size, you want to control the first before touching the last. That was one of the lessons, right? You really can't control effect size. Effect size is the term for how big is the effect I'm trying to study. How much as I change one variable does the other change? That's built into whatever underlies the problem, so it doesn't really change what the effect size is. Sample size, I can't control. How many people do I sample? But that can be very expensive to control. So variance is our best choice of what we really want to deal with. Now, you can get a different effect size by changing what your model is and looking at things differently, but that's a much more subtle place to go. You don't want to change your theory right now. So if I look at the algorithms, a slightly different way of adjusting. So if I could try and say it's a trend, right? So I could just try and guess what that trend looks like. But another way is to say, let's look at the difference between two algorithms. We call this a match pair test, okay? Sometimes just called a pair test. So instead of looking at the algorithms by themselves, I look at the pair. I'm going to look at the reinforcement learning versus the SVM and subtract them. So if there's a trend, I'm looking at the difference between them. Right? So now this is far more flat than the curved pitches we had before. And if I do that for all the data compared to the one we had before, we get this sort of patch. We get a much lower trend. So we've now removed the trend. So this is an easy way without any known model to reduce trends. It's just to do a pair analysis. Take two pairs. There's in fact a particular statistical test where I do paired testing. It's called a paired t-test, which we'll talk about, right? And a paired t-test, I can now look at that, and this difference is now significant. This difference is not. That one is. But as soon as I do that kind of pair testing, the fact that this line is above this line everywhere in multiple places produces significant results. This one's still too small to be different, but the other ones may or may not be. And one of the things you're not seeing here is, right, this was where we took binning, we put a bunch of data together. So each of those bins still has variation, which is actually like in here. But now that variation is smaller compared to the differences where one of them is on top more often than the other. So coming back to the lesson of demonstrations are nice, but explanations are better. While this is answered that the reinforcement learning was significantly better than the others, right? It really doesn't answer why. Why is it better? Is there something that's really going on? If it's not better at all levels of training, which it wasn't here, right? Is it really still an artifact of the small samples of data we had? So just because something is statistically significant does not mean it's random, right? So the jelly bean example, right? If I ask enough questions, I might get something that's random, that's actually random, but shows up as a result. So we have to be careful. Why does this curve look more straight than these, right? Those are questions. When you're analyzing your data, asking yourself those questions, there's something I don't expect here. Those lead to new insights and new questions as you're doing your research to go answer that. Another one of the lessons was that most interesting science is about interaction effects, not just the main effect. So if I looked at the system performance at greater levels of knowledge when learned knowledge is included, only when engineering knowledge is included. So I can look at a knowledge base where it's engineered knowledge versus incrementally adding data. Learned knowledge has the advantage that once I've learned knowledge, that often makes it easier to learn more knowledge. From a human point of view, that's well known. Right? The more I know, the more connections I can make between things, the more I can learn effectively. So if it's true that the systems that have learned knowledge learn in part because they learn more, then these lines should not be parallel, right? Because if they're not learning at a constant rate, one of them is learning faster, which is what the theory suggests. If the amount I know allows me to learn faster, then the more I learn, the more I can learn faster, which means I should see an increasing line, not just a parallel line. So that suggests now a hypothesis. We can go back and test, are these lines all the same? Okay. So in this case, right, the reinforcement learning is a straight line. The other twos have a faster amount of learning in the beginning and then level off. Now, very small amounts of data, hard to answer whether or not this is hitting. So if we wanted to look at doing this, the answer for this one is this doesn't have enough data. We can't answer whether or not we should have gathered that data. So when we're looking for explanations, after we've looked at our data, this is why we often need a pilot experiment, we might say we do not have enough data. We have to go out and measure more to answer that new hypothesis. Now, if we had started off with that hypothesis about them being parallel earlier, we might have said, fine, we're going to break it up so we can explicitly measure that. So I might need more bins this way, because with 3 lines, it's really hard to talk about the change in slope. They really have one slope and a second slope. There's just not enough information left. We needed more bins down here, but there simply wasn't a lot of data to do that. So you want to figure out how that's going to go. So if I look at modeling, there's a whole bunch of variables in terms of how well we fit it, the degree that I fit it with. If I wanted to fit a quadratic and say, I expect quadratic growth, 3 points is the minimum. They define exactly 1 quadratic. We have no noise tolerance or anything else, right? So thinking about what your model is affects how you want to fit your data. You can't account for everything by just reducing variance. You still do have to take into sample size to make sure you sample in your independent variables enough to get the dependence that you need to measure in your models. Significance and meaningful are not all the same. So again, just as basic examples, if I look at the reduction in uncertainty due to knowing the algorithm, we'll talk a little bit more about statistics again next class, but if I look at how much of the variance, we talk about the amount of explained variance. So here's the raw variance. Here's the variance after I know what the algorithm is, and I can divide that by the original variance, right? So how much of the variance happens just because I know which the algorithm is? And we call that the W statistic. So if I look at the reduction, I can talk about what that reduction is, and we'll see that we get for our fully trained algorithm with a lot of data, I get some reduction by knowing what the pairs of algorithms are, but that doesn't really answer our question, right? So is this different? So we said back here, right? This difference was statistically significant, right? This distance was statistically significant. So rel versus KB was statistically significant. But if I look here at the W statistic, the amount of explained variance is only around 20% of the variance. There is still a lot of variance in this problem that is not accounted for by knowing what the algorithm is. Or actually down here, it's 34%. So still a lot of the variance in that algorithm is not explained. So this has not allowed us to answer meaningfully, is this really better? So the result was statistically significant, but there was still so much variance that this is a weak place to get into your conclusion. So review of the lessons that you want to go through, right? So evaluation begins with claims. Metrics are meaningless. You have to have claims to go with them. The task of empirical science is to explain or reduce the variability, so design to do that. Humans are a big part of our variability. Of sample variance, effect size and sample size, control the first between touching the last. So find ways to reduce that variance. When you're working with humans, I forgot to mention this one on that slide, a lot depends on the instructions you give them. Slight variations in those instructions can produce significantly different results. And 1 or 2 unanswered questions can make the entire experiment completely invalid. One of my 2 psychology experiments in my thesis, or 1/6 of my thesis, was completely useless because after I gave my people instructions, I ran a whole bunch of people through. Each person did 2 hours worth of experimentation. I ran like 2 dozen people through. And in the end, I learned that all of my conclusions were completely useless because the humans were keying off of visual features that I had not mentioned, that I didn't think they would use, that I didn't even think about. But that's what drove their conclusions. And so it's like, okay, this is completely useless. Right? I have to run the experiment again. One of the things I recommend anytime you do an experiment with humans is you get 1 guinea pig subject who has to approximate your pool and have them do the experiment and then have them talk about everything they can think about while they're doing the experiment. So basically, you turn on a recorder and you have them verbalize aloud while they're doing stuff so that you can learn what their processes are then analyze that to see if there's any missing things. Because the number of experiments where people have made decisions in their processes not the way you thought they were going to, that make your experiment pretty bad, okay? It's too painful. And if you don't get the instructions right, you have to be very tempted to, you see them doing it wrong, it's too late. They've already interpreted your instructions wrong. You have to now get a new subject, start over again with new experiments, new instructions, and then test them to see does it work. Right? And before you scale up, this is a really important part of any experiments with people because they will drive you crazy. Demonstrations are good, explanations are better. You have to make that determination for your project. Can I live with just a demonstration, or can I actually drive an evaluate explanation? My recommendation is you always aim for an explanation. You only settle for demonstrations when your explanation is not consistent with your data, but you still have a good demo. Then just go with the demo.
Wait a minute.
Well, so
I'm reading 0.5 now.
What I was like, I said the answer is like we've had a couple of good papers where it's like, here's the results, and we originally thought it was that, but it's not that. We're not sure what causes it, right? There's nothing wrong with that kind of thing. If the results are there, but you don't have a good theory for them, it doesn't make them not interesting, right? Maybe it'll fit somebody else's theory. Maybe they will find a way to make it good. But if you're demonstrating something that's actually useful or novel and no one's ever seen it, then it might still be worth doing. Now, or you can take it back and say, well, I'm going to keep running experiments until I get it right. That's a question of what's my next publication deadline, my graduation deadline, what do I have to get done, right? There's pragmatic choices to go into that. So most explanations involve additional factors. Most interesting science is about interaction effects, not the main effect. The other good thing about looking at it this way is when you can start telling a story about something that people don't expect, right? That fits in naturally with the storytelling narrative we've talked about and the idea of sticky stories, right? Because they weren't expecting that effect. So that's the surprise that makes it much more interesting. Look through the data to figure out what's going on. Not all studies are experiments, not all analyses are hypothesis testing. I didn't go into that, but anytime you have some chance for some theory, there are lots of areas of computer science where if you can have lots of equations, your papers are treated more seriously, even if they're not actually more serious, but you can add math to your papers to make them seem a little bit more serious. But that's because over a long period of training, people have learned that lots of good theory actually does help. When you have a theory, and a strong theory, and math that helps explain it, it makes it easier to reproduce, easier to prove various things about. Okay, so now experimental design. Okay, so I thought I took all these out. These are really nice. Give me a second. Select all.
Are all the following slides going to include
I accidentally clicked once on that subsection of slides and like chose whatever the transition is. Yeah, effect. Please select all in this version of PowerPoint. No, that's not it. Slide sorter do it Is it transition? No, is that animation or transition? Animation, advanced animation, none. Oh. I don't know if that fixed it or not. We'll see. There must be a way to apply to all because I've done it. I just don't know how to undo it. Okay, well. Okay, that works. Just go faster. Okay, so experimental design is all about how do we choose elements that go into what makes our experiment. So if I'm doing experimental research, the simplest form of looking at this is I claim a manipulation of A treatment variable, which we'll call X, the treatment variable, followed by an observation of a response variable Y. Right? So these go by different names in different areas. We can talk about a treatment and a response variable, which is more on the medical side of computer science. I can talk about an independent and dependent variable. Right? They're really the same thing. And I like to make sure we just cover all the different terminologies so you sort of get it. It's actually easier to think about this for many people if I think of it using the terms treatment and response, because you can literally think of it as, okay, I give somebody a drug, and do they recover or not? As opposed to I change an independent variable and there's another one that's dependent. It's easier to keep track of whatever it means. So the experiment has to be designed to control for other variables to establish the causal relationship. So our goal is to drive an experiment that really lets us reach a causal or closer to a causal relationship. And we have to remember that experiments can only reject high hypotheses, right? Experiments can't prove something, they can only prove it's not true. Because I can observe something that's inconsistent with the hypothesis. I can continue to observe lots of things with a hypothesis, and I can just, right, if I don't go far enough, I don't get there, right? Because otherwise we could decide that all odd numbers are prime, right? 1's prime, 3 prime, 5 prime, 7 prime, I'm done. Okay. So you gotta disprove them. So people will do what's called descriptive research. It provides a snapshot of some aspect of a system at some point in time, and there's no real true causal hint, no hint of a causal insight that can be attained from descriptive data. Well written, you may convince people of an incorrect causal link. You may even delude yourself. But if you actually haven't designed it for an experimental analysis to say, is it causal, you don't know for sure what the causes were. So I like to recommend you don't aim for descriptive research. Descriptive research is what you end up publishing when you failed to reach the causal conclusion you hoped for. You should aim for causal. You should test for causal. And if you can't, talk about it from a descriptive research point of view. Because you can still tell the story of what it is. It's actually good, in my view, to start with a hypothesis in the story. You're going to go out and test it. What you want to test it from the point of view is, does it cause it? So to answer that, we have to answer, what constitutes causality? So what do you think is causality? What do you think defines causality? Okay. So having an effect is a little vague, but I'll give you, you got most of it. So the important thing is that a change in one variable, oh, this is quiet this time, will produce a change in another, right? So it has to produce a change, right? So an effect, right? Is an effect a change? Well, right? The effect might actually be not causal, even though I perceive it, right? How could that happen? How can I have an effect on somebody, but not actually be causing it?
There's a variety of ways associated with that. One is that you may be influencing another variable, which is the actual cause. There may be something else going on, like your example of the fact that in the summer it's hot and people go swimming and drown as well as eat ice cream.
Mm-hmm. Right. So in fact, the ice cream example, right, is right. It is hot. I eat ice cream. I go swimming. So eating ice cream precedes it, right? And I drown, right? So when I drowned, there is ice cream in my stomach, right? So is there an effect? Yes, but it's not the cause of the drowning, right? In fact, I might cough up stuff, right? So there's lots of things. So there's lots of things where there's a temporal correlation, right, and an effect, but the effect is not the cause. The effect just happens to co-occur, but it doesn't make the person drown. And so that's where you can get a difference. So that the cause is it produces a change, right? One variable will produce a change in another. So that's causal between the variables. So we talk about the concept of preconditioning influencing a variable of interest. So the drowning, if that's the variable of interest, I have to influence the actual outcome that I'm interested in, not just affect the state. I have to influence the outcome I'm looking for. And there has to be the sequence of time. And importantly, and this is why the effect is too weak, is there really has to be no other possible explanation. Right? So it's not like I drowned for some other reason and I happen to have ice cream. Right? There's no other explanation. Right? So if I can't keep being on that, I can't find another connection there, but right? If changing this variable will always lead to this, then there's no, but no other possible explanation doesn't mean it always happens. Okay? This makes it harder. I don't mean to say it's like when this happened, this always happens, right? It could happen that if I'll do this swimming different way, right? Lots of people believe that if I eat right before I swim, right, I am more likely to have a cramp and drown. Okay? Statistical data shows no such correlation exists. Okay? And yet it's widely believed that this happens. Okay? And oddly enough, there is a relationship. There is a causal relationship for a very small subpopulation for whom their blood flow is insufficient, that when their body is digesting food, they no longer have enough blood flow in their extremities, and they will get a cramp and die, right? But it happens only to a small subpopulation, not to most people. That's why you don't see a statistically significant result. If I were to do this to people who are anemic, then all of a sudden it becomes a direct causal, right? It's like 50% of the time this will happen, but they're 2% of the population, right? So you have to think about, the fact that there are no other explanation doesn't mean there are other variables. There are no other variables. So I might have to find the right subpopulation before this will happen. So if I'm playing with computer science stuff, it might be that there is a causal effect for one type of data and not for another type of data. That doesn't make it not causal. It means it's caused when this occurs and something else, right? So causality then becomes a question. Do I have all the conditions necessary stated or only some of them? You have to figure out where that's going to be. So we can talk about things like the difference between attitude and behavior, right? Attitude causes behavior. It's a causal link people often talk about. Or is it the other way around? Does behavior cause attitude? Right? So, so we talk about this idea of the direction of causality, right? And determining the direction of causality literally depends for almost everything on your theory. So whether or not attitude is causal of behavior or behavior is causal of attitude depends on the logic and the previous theory you're looking at. So if I'm working from social cognitive theory, right, which is a particular psychology theory, then that arrow goes one way. If I'm working from behavioral theory, it goes the other way. Right? So which of those is right? No way to know from that, right? According to one theory, one is causal. Now, is there a way to actually prove one theory? So can I prove one theory? No. Can I disprove it? Yes. Because if they're truly causal, there's always a temporal arrow. Causation happens, right? One of it happens, then the other has to follow. So if I can show that they go in the other order, then I can show that in that instance, that theory is not correct because it's no longer causal. Unfortunately, when I have lots of people, and this is why so many psychology theories seem to contradict each other, different subgroups can be different. Right? And so it may be that people who have certain conditions behave this way and people who have other conditions behave that way. So you have to be careful. If a time lag exists between cause and effect, then the causal variables should have a positive association with the effect. Positive here, not necessarily in the direction, but just the fact that there is a cause in the lag variable. However, temporal correlation is not causal, but people often assume it is. So if you want to write in such a way as to make people think things are causal, write them as a temporal order, right? And people will think about this. We already discussed this, like, John's car is parked out front. You instantly connect things in time as a causation and a relationship. So it's a natural part of storytelling. There are times you want to take advantage of that. But when you're designing your science experiments, you don't want to depend on tricks. You want to not fool yourself. You want to do it right. And then afterwards, if you have to, tell a story. In computer science, there's a whole body of research on causality by a guy named Judea Pearl, one of the Southern Californians, USC, UCSD, one of those guys down there. So he's the father of causal reasoning within AI. And basically, they came up with this nice formal logic, which is a generalization of earlier formal logic for causality, where basically, in these rules, an arrow defines the direction of causality, and we have unidirectional arrows. We basically have things called nodes and vertices. The names of those names and vertices should be clearly understood by the people, so in your diagrams you can talk about them. We display along a time axis, which is generally left to right or top to bottom. This is sometimes too complex, so you can actually say this is a timeless diagram and it's just the order of arrows, they're asynchronous. You don't know what time is. But generally in this arrow, right, so this is time. A precedes C, precedes D, E. But since it's directional arrows, it's pretty clear the order they flow in. The only question that wouldn't be clear is, does B happen before or after C? Right? This is actually saying B happens before C. It could also happen over here, in which case then you don't care about what time it is, right? Could D ever be after E? Right. Because E is causally linked, D causes E, it can't be after in time. Right? So there is an implied ordering in the way the graphs have to lay out. This is why we don't actually have to have hard timing. Variables are what we want in our diagram, not values of variables. So if I have something like parallelism or complexity, that would be okay. But it wouldn't be okay to have O of n or 128 nodes, right? We don't have values, we have variables. And this is actually difficult. Some people like to stick in here things where they take the value of a variable, like not parallel. Okay, well, parallelism is a variable. Not parallel is a value for which the state of parallelism could exist, right? If I want to say there's causality only when something is not parallel, right? I have to have parallelism in my value, and then the arrow is going to possibly go multiple places. And so that becomes more complicated. So they don't normally show up in a causal diagram. So when we talk about our basic rules for our causal diagrams, an arrow, a postulated cause and effect. We don't have bidirectional arrows, right? Because we don't have bidirectional cause and effect. A doesn't cause B as B causes A, right? We can have effectively A and B both correlated with each other. We don't know which is causing it. So if I had C causing A and B, right, then it may look like A and B cause each other. Because when I see one, the other happens. Whichever one I do, the other one happens. But that could really just because if I do A, that causes a C, which causes a B. If I do a B, that causes a D, which causes an A, right? So there's an indirect link between them, but they can't be directly linked. We have this idea of an arrow with a question mark, which means that's our hypothesis. We want to try and do that. And whether or not that occurs will depend on our theory and our axiomatic stuff and what we're trying to do. So when we think about these for causal instances, we want to think of conditions for our concatenate variable, right? Evidence suggests there's a relationship between what we observe and what's happening. Conditions on time and order of occurrence, this gives us some idea of which ones have to occur and which ones might be causal, and the absence of a compelling causal explanation. So if there's no strong relationship, there's probably some higher level variable that's causing this. I can't think of why they're correlated. So as I'm doing my experimental analysis, I'm going to look for some of these things to help define what are my causal relationships. But after I've done a little bit of exploratory analysis, I can write down one of these diagrams and say, here are the things I think are causing them. Right? And I actually recommend you go through this formally. Most people, most students, when they first start, want to have hypotheses in their head and then go design their experiment to go test them. Right? And that's perfectly good, but I think it's much better if you learn to formalize them, write them down, and if you don't like this notation, you can still write them down in just words. A causes B. If I make this change, here's the hypothesis of what's going to happen. So this is related to our hypothesis. It's just using a more dense notation so that you can sort of make these hypotheses. But these important constraints, right, should be part of what goes on, right? You can't have bidirectional errors. You can't have cause and effect going in both directions. And you want to answer, this is the cause I'm trying to test. And that's going to show up when we get to our experimental research. Because if my goal is to test whether or not A causes, if my goal is to test whether or not A causes B, even though C can cause A and C can cause B, what do I need to do in my experiment? Well,
see if there's some other thing that can cause B and not cause A.
Right. So if I had some way to cause B without causing A, right? But one of the things I would have to do is I would have to make sure that I'm not using C, because if C can cause A and C can cause B, then I have to make sure there's no C in my system if I want to test whether or not A will get to B, because C is a confounding variable, and as it changes things, the rest of my experiment, I'll never be able to tell. I keep getting A's and I keep getting B's, but I don't know if A's are turning into B's, right? Because C is out there, right? So this is why it can be really helpful. Is it's easy to ignore some of the interactions between things until you write them all down and try and formalize them. So if these are your hypotheses, writing them down will help you design the right experiment to test whether or not your idea is right. And there's actually nothing worse than doing an experiment that you think shows this, and then having a reviewer say, well, these could both be caused by C, in which case your paper's done because you haven't ruled that out, which might have been easy to rule out if you design it that way, but it's too late at this point. Okay, so issues in experimental research. So when we're talking about what type of experimental design we should be using, we want to start with design anywhere. We start with designs involving humans, and then we'll deal with some pure computational experiments. Dealing with humans is much harder. If you understand how to design an experiment that involves humans, figuring out how to do pure computational ones will be easy. Right? We're going to start with those first. Sometimes the things that we think involve pure computational experiments turn out to have humans. So if I'm looking, for example, at network traffic, I might think that's just humans. I'm sorry, just computers, right? It's just data on my traffic, data on my network. But the answer is, if it's data on a network, there are humans somewhere on the other end of those keyboards, right? And so there really is, almost most of it, right, human effort. And so all of these that go into designing for humans apply. If you're talking about a computer, I'm looking at timing results. I might say it's just speed. But if I want to talk about speed with respect to realistic human users, there's realistic human users behind that. So there's lots of things where we often try and extract them. So an important question is, should the experiment be performed in a laboratory setting or in the field? We'll talk a little bit more about that after we get through all the designs. But laboratory settings have what advantage? I can control stuff. What is the advantage of in the field? Right. It's more realistic, right? I didn't control everything because I didn't know what was important, right? So in terms of, well, so that's the field. In the field, the natural variations are really important. The bad thing is you don't control them. Yeah, so it can work in the real world, right? As opposed to, look, it works fine as long as I have an optics bench. So you got to figure out where this is going to be. So what's the right answer for the experiment? It actually depends on the stage of your research, right? If you can't get it to work in the laboratory, does that mean I shouldn't work in the field? So, and that's the natural answer, is why I asked this question. My recommendation is try both early. Don't view it as I got to get it to work in the laboratory and then try in the field, because there are a few things that have worked better in the field than in the laboratory. Because your model of what should happen in the laboratory is actually not, it's missing stuff that actually makes the real problem easier. But you didn't think about it that way.
The other aspect of that is sometimes you'll encounter errors in the field that allow you to address earlier in your experiment.
Right. So if your laboratory experiment was based on the bad model of the field, seeing that early can really help. But there are times when the solution in the field turns out to be much easier because you didn't think about the problem the right way. And you abstracted it away into the laboratory setting. In the laboratory setting, you get this nice, crisp, pristine behavior, right, that makes the problem harder, because you don't actually have to make the decision based on the variables you were limited to, right? If I literally observe humans in the field, they might be telling me what the solution is by not using the variables I thought they were going to use. Right? People don't always use price information to decide what product you want to do, right? There's a lot of human emotion and stuff. So that will affect what's going to happen. Humans make decisions based on what other humans in the field made. So if people can see other people, their behavior may not be as complicated to model as you think. Once I get one transaction, anyone who's watching them may be influenced by that. You get a whole bunch of interesting effects.
For clarity's sake, even though observation is considered an exempt part of research studies for humans, it still has to go through IRB to receive receive said exemption.
Only IRB can decide that your work doesn't need IRB. That is correct. With that caveat, with that though, I will make two other observations that are a little bit simpler.
No, you can't do any observations. We already established that.
So, if you are observing data in public and you want to publish it, so the next question for IRB is it research? Right? If it's not research, you can decide you're not doing research. Right? Because if you have no goals of publishing it, if it's not supposed to be generalizable information, then it isn't research. Right? And
I don't wear my researcher hat, I'm okay.
No, if you're not wearing your researcher hat, you're okay to observe people.
Yes.
It's only as a
Once
researcher.
you put on that hat, you're in trouble.
But I can observe people. So, for example, if I collect YouTube videos and I watch them, right? That's not observing people. That's observing YouTube videos.
Interesting.
So abstracted data, right, that isn't humans anymore, right? Maybe completely exempt because you're not observing. You're not designing an experiment to collect human behavior. You're just analyzing prior data. Now, we can still get into a big fight. There's some IRB people that say, no, even that, we're the only ones who are going to decide whether or not it is. But we've also gotten plenty of permission. So when we're doing business studies, right, because we're doing the BI stuff, right, when we're just looking at customer preference for a business, and we have zero interest in publishing it, it is not research, then it is not subject to IRB. I can help a company determine the price.
Kind of hilarious when you have like Google going to Atlanta and asking homeless people for their facial recognition pictures, not telling them what it was actually used for.
That's a business decision.
But it's a business decision. It's not IRB,
research.
but that's totally cool because it's a business. They're not going to be publishing any of their IP that they get from it.
Yeah, but Congress will get them later.
You hope.
So if they ask the homeless people, it's a different category. If they just observe the homeless people, right? I just full disclosure, you guys know about my difficulty with facial recognition or not? Oh,
This is interesting.
I know that the smokestacks caused you problems.
Oh, that was a different set of. It was actually facial recognition research then, but no. There'll probably be an article in whatever the name of the campus paper is, the Scribe or something like that.
Oh, I have heard of your research. You watched people and like took pictures.
Yeah, we took pictures of people on the sidewalk, right? Yeah.
And that ran
Public
foul.
space.
Public space, yeah. So, and IRB actually approved it. We went through IRB. It was all the standard process. Why? Because we're just observing people in public, right? We're not doing anything, right? We have no idea who they are. We have no idea what their identity is, right? So the data doesn't have identifiable characteristics. It's just their face.
You know of.
Actually, so
I mean, you could like facially recognize other people now if that was pictures in the database.
the current U.S. government definitions of facial biometrics are they are not private information. So there's no private information, right?
There's a gap. Like there's a gap between what consumers would want and what the regulation actually does.
There's a lot of gaps.
There is a lot of gaps, but like, would you
Find
argue
the
there's a gap?
I would argue that your face in public, right, if it's not tied, so I don't get to know who you are or anything else about you, that's the definition of public.
So let me ask you a question because I've thought about doing this before. Let's say that we have, say, sculpture or something like that in a public area. So falling under the caveat of art, that happens to have a camera on it. What that camera does is it facially recognizes you, and then conducts an internet search of you, of that particular face, and then displays the result on another part of that sculpture. Would that be something that would require
IRB?
That is
No.
so great.
As long as I don't publish, that's perfectly okay?
Well, so I would argue that if you
Under the venue of art, it's an artistic expression.
as an artistic expression, so because you're not trying to do research, right? I would recommend, however, if you're going to do that, you go get IRB and to say that you are exempt from IRB, which is actually what I did. IRB is covering my protocol of taking photos of people on the sidewalk was exempt, right? Which isn't right, right? Then when people complain many years later, right, and literally try and sue you, it's like, look, we follow the proper protocol, right? It's
Talk to IRB.
Yep.
No.
Panel.
It's not even talking to panels. Like the panel agreed. This is the current law, right? Video surveillance in public is
As long as you don't capture sound.
right. As long as you don't capture sound, right? So that's true in every state in the nation, right? I can videotape you anywhere in public, Right? Now, there is some gray areas. If I videotape from public through your bedroom window, that's not considered public, right? Even though I'm in public, right? Both the receiving person, wherever's being videoed, has to be in public. Doesn't matter where the camera is, right? I can record from private to public, but I can't refer from public into private and consider it public. So there's a whole bunch of laws that you have to understand to follow that. But I recommend if you do that art installation, one, it could actually be interesting. You'll definitely get some press for it. So if you want to become a famous artist, which to be honest, all of my difficulty with my facial recognition came because a privacy artist decided to take interest in our work and started pushing for publication of articles to beat us up for doing things that was perfectly legal, in which
But ethically questionable.
Well, I think that we're moving faster than we can really make policy for. So like normally it'd be like, oh, you're photographing people in public. All right, no problem. Then you put it into a database and you give it to other researchers. Now you have ImageNet, and you didn't tell any of those people that it was putting in a database that is going to be used to train algorithms.
Or say that you have multiple art installations, and that art installation says, hey, I saw you last time here.
Yeah, obviously you're in a database somewhere.
so there's already been one of those. we literally did an art installation where we detected people,
Oh, yeah.
and then in one part of the museum you were being detected and you were being projected in another part, which you could have also been projected into another art museum like in Alaska from Peru.
Oh my.
Right? So you're like seeing other people watching art, watching you, watching art.
Very meta.
Yeah, very meta. That's what the artist wanted. But yeah, so whether or not it's a database and what gets used with it, so there are some ethical questions, right? So we can get into, and it's not today's goal.
Sorry.
That's okay.
Sorry.
Actually, no, I'm just thinking about like how much I have more to cover. It might actually be better to just finish the discussion with this, and then do this next topic, because I was going to go through all these different experimental designs. So and there's a lot of them. So we might want to say, we'll just do that. So we'll just continue this discussion and we'll kill off the video.
This tied to the earlier presentation.